Hi, AP Calculus students. This is the video for 3.7, the examples for section A. I was going to do one whole video and then Zoom stopped. Luckily, after I got the notes done, so I'm now creating a 3.7A examples video. And so let me make sure, I think I could have done a better job getting this right. So we're going to do 23C and number 16 in this workspace here. I may have to do some work and erase. So please be sure to write everything down because it may not always remain as we do more work. So this is on 23C, right? We have the list of all the steps that you took over here, and I'll be saying those steps as I do them. So on 23C, the question was, find the maximum volume of a box with a square base. Notice I made a square base. I did mark those sides X and X, and a surface area, that's what the SA is, of 150 inches squared. So what I did is I made the distance between the front and the back base H. And so the first thing we do is identify all quantities given and to be determined and draw a picture if possible. That was our first step, and we did that. Then B, write a primary equation to maximize or minimize it with a feasible range. Domain. But anyway, so I need to write the volume formula for the box I see. And I am going to remind myself, I always mark it that I'm looking for a maximum here. And that would be X squared times H would be the volume of this box. Now, because we are only going to have one independent variable, and we have two, that means that I have to eliminate one of the variables. And I am going to use on letter C, secondary information to do that. Here is my secondary information. I have been given a certain surface area and I want to maximize the volume of this box with a square base, right? You can see given a set of materials where we might want to maximize that volume, right? So this is my secondary information that I'm going to use to substitute this H out of here just for, so I only have X's. So the surface area is equal to 150 inches squared. Now, let's write the equation of the surface area. The surface area of this box, there are 6 faces that make up the surface area. There's the front, right, which in that surface area is X squared, and there's the back that matches that. So 2X squared, first of all, is part of the surface area, the front and the back. Then I have the 4, they're called lateral sides of these rectangles that have an area of X times H. So I have 4 of those, 4X times H's, right? So what I'm going to do here is work to get the H alone and then substitute it here. So that would be 150, and I'll subtract the 2X squared. And I will divide by 4X, right? So let me just make sure I did that right. Right, that would be my H. And I am going to put this expression right in for the H, okay? So my volume is now equal to, I have this X squared times 150 minus 2X squared over 4X. Okay, now, so this is my volume formula that now has one independent variable, right? But this is kind of messy to take the derivative of. I think I can clean this up a little bit so that I can take the derivative. Notice that this X cancels out and leaves 1X here. And I think it might be nicer if I break this into 2 pieces, right? So I am going to distribute the X here and here to the 150 and to the minus 2X squared. And I'm also going to split up these 2 pieces so that maybe I don't have to have a quotient rule, okay? So let's do those 2 things together. So 150 divided by 4. Let's see, I can divide, let's see, that would be 175 halves, right? If I reduce that, so 75 halves times x, right? So 75 halves times x minus, this is going to be x cubed over 2, right? Because this 2 cancels out and leaves a 2 in the denominator. So minus x cubed over 2. Okay, so here is my volume formula. I'm going to come back up to the top. I'm going to replace this, and then we'll take the derivative and go from there. Okay, so 75 halves x minus x cubed over 2. This looks much better to me to take the derivative of. Okay, now, next step, let's take the derivative, right? Because we're trying to find a max or min, and the derivative would occur at a critical point where the derivative is 0 or undefined. So let's take the derivative, and that would be 75 halves minus, I'll bring the 3 out front and multiply it, 3 halves, and reduce that exponent by 1. There we go. Let's do critical points. Undefined. This is quadratic and is defined everywhere. Where is this equal to 0? Let's find out. Okay, so here's the derivative. Where is it equal to 0? Let's see. I am going to subtract a 75 halves from both sides, and I'll have a negative 75 halves equals a negative 3 halves. So I am going to make both sides positive, okay? So I have 75 halves equals 3 over 2 x squared. Okay, again, I subtracted 75 halves. I had a negative on both sides and made them positive. Couple ways to go here, but I think I'll just, I could cross multiply, right? 6x squared equals 150, right? And I will divide both sides by 6, right? So x squared equals 25, right? 150 divided by 6 is 25. And we'll take the square root. Okay, so that happens at plus or minus 5 for a critical point. That's where the derivative is equal to 0. Of course, we're not going to include the negative 5, right? This x is a side of the box. There's no way it's going to be negative, so it's 5, okay? Now, let's talk about this for a second. The x, the maximum for that side is going to be 5, okay? But we are still going to go ahead and do our first derivative chart and make sure that 5 is a maximum, okay? How do I know that that critical point where x equals 5 is not a minimum? Because I know what the minimum volume is. The minimum is 0, making a side of x of 0. I know what the minimum is, right? But we will still do our first derivative chart, right? And we will talk about, let's talk about the feasible domain before we do our chart. We are looking here at what x can be, right? So x, because it's a side, isn't going to go from negative infinity to infinity. It's going to start greater than 0, right? If you have a side of 0, you don't have a box. So the domain so far is going to be from 0. Now, what logically is the domain gonna be? We won't come up with a specific number. We'll put to infinity, but let's face it, if the surface area is only 150 inches squared, let's think about that. What is the most, right? About the square root of 50, right? As the square root of 150. Right? I can't, obviously these sides can't be, 100 and 100, right? And even if the height were 1, that's too much surface area, So really, when you think about it, just the sides, the front and the back being 2x squared, right? if you made just those two sides 150 inches squared and didn't even like just had a really small lateral area. So the base, you made the bases really big. So the 2x squareds, the front and the back, would equal the 150, right? Surface area. So when you divide by 2, you get x squared equals 75. And when you take the square root, right, then you get 6 point something, right? So, I mean, feasibly, this x really can't like be more than 7, 8, you know. We'll put infinity because it's not really necessary. We're just looking for that. But I just wanted you to know it's probably between like 0 and 8 is the most you could have, right? Or so, 8 or 9. All right. So let's go ahead, and I have my critical point of 5. I'm going to start my domain at 0, go to infinity. So let's go ahead and do that chart. We know x has got to be a maximum, but let's show that it is. Let's go ahead and do that. Okay, so here's our first derivative chart. All right, so our first derivative chart then, my intervals, right? My x would start at 0 and go to 5, then from 5 to infinity, or you could even stop it at 8, 9, or 10, anything you want. Test value, let's put in a 1 and a 6. And the first derivative then, let's take a look. The first derivative, oh my gosh, did I actually erase the first derivative? That's just wonderful. I'll rewrite it. What was that first derivative? 75 halves minus x cubed, 3x squared over 2. Sorry about that. Was trying to save space, you know. Okay, when I put a 1 in, 75 halves minus 3 halves, of course, is positive. When I put a 6 in here, that's 36 times 3. That's, 90. 36 times 3. Yeah, that's, 108 there. Over 2 is, of course, much bigger than 75 over 2, and it's going to be negative. So I have actually proven that logically what I know is that x equals 5 is a maximum because it increases before 5 and decreases after. Now, let's see. We've talked a lot of logic here. So on E, check your solution with logic. We've checked. But let's make sure we're answering the right question. Did they just ask us for the dimensions of, did they just ask us for the side? Did they ask us for the dimensions? Did they ask us actually for the volume? So let's take a look. On number, that was 23 that we did, determine the dimensions of the rectangular solid. Okay, so the dimensions are, I'm going to erase again, right? They asked us for the dimensions. So the dimensions would be 5 by 5 by the height. Okay, well, what is the height? Oh, well, I can figure that out. How do I figure that out? I figured it out because I had the surface area. The surface area was 150, right? And that was 2x squareds, 2 squareds plus 4xh. So let's go ahead and put the 5 in for the x, and then we can solve, right? We can solve for the h. So let's see, that's 25, that's 50. Plus 4 times 5 is 20h equals 150. So let's take a look. When I subtract the 50, I get 100 divided by 20. Oh, this h is also a 5. Again, doesn't this make sense? Let's talk about that again, right? How, when you have a given area, like a rectangle, how do you maximize that area? By given a certain dimensions, you make it a square, you make it a regular polygon, okay? When you have given certain information, like a surface area of 150, given a certain area and you're making a box, how do you maximize the volume of the box? You make it regular, you make it a cube, 5 by 5 by 5. So that this all like is coming together, it makes sense, okay? Let's do problem number 16. Of course, it's a minimizing problem. Number 16. Okay, let me write that. On number 16, they give you a function, f of x equals the square root of x minus 8. And they give you this point 12 and 0. And what they want from you, it says find the point on the graph of the function. Find point on this function that is closest to that point. Well, that's an interesting question, right? So on this function, they're asking us to find the point that is closest to 12, 0. Let me help myself out by drawing a picture of what's going on, okay? So here's what I kind of know. That this is, I know what the square root function looks like. And let's do by 4s, 4, 8, and 12. And it's been moved to the right, 8. So it looks like this. And they're giving us the point 12, 0. And they want to know at what point on this graph is 12, 0 closest? Like, would it be here? Would it be this XY point? Would it be this XY point? Would it be this XY point? Which one of these, like if I drew the line connecting to the point on the function, would be the smallest? So what is it that I'm trying to do? What I'm trying to do is minimize the distance from this point to a point on the graph. Okay. Now, just so you know, I can do a little better, you know, than just calling it an XY point on the graph, right? So let's say I pick this distance right here, right? The point on this graph is not just some XY point. When I take this X and put it into this function, it gives me the Y, right? So the Y I know a little bit more about the Y. It's the square root of X minus 8. That's what that Y is. And this point is 12, 0. So I'm trying to minimize the distance between these 2 points. Well, let's use the distance formula, right? So the distance formula is what I'm trying to minimize, and that is the square root of x2 minus x1 squared plus y2 minus y1 squared. This is what I'm trying to minimize, okay? So let's just call the point that they gave us, let's call this the first point, not that it matters, it'll all work out the same, and let's call this the second point. So here's my my x2 right here, so here we go. So x2 is 12. My x1 is an x squared, plus my y2 is a 0, minus, and my y1 is right here. Okay, so I'm going to go ahead and actually FOIL this out. Notice this 0 I don't actually need. And so the distance formula I'm trying to minimize is, let's take a look here. This is 12 times 12, 144, minus 12x is minus 24x, plus x squared. And when I square this negative, it becomes positive. And when I square the square root, I get x minus 8 left, right? Because the squared and the square root cancel. So this looks like, probably like, oh my gosh, wow. You know, this is interesting. But let's just clean this up a little bit more, and then let's talk about it. So we have x squared, right, minus 24x plus x is minus 23x, right? And then 144 minus 8 is 1, did I catch it all? 144 minus 8. I'm doing okay. Ms. Culver needs a nap. 6. I just want to make sure is 136. There we go. Okay. Now here's what I'm going to do. This sets at the bottom. I'm going to erase. We kind of know what's going on here, what we're trying to do, right? And so I'm going to bring this distance formula up and talk about it, because what we're saying is I'm trying to minimize it. And that's a lot that's going on there, right? So I'm trying to minimize this distance formula. Okay, now, so we want to take the derivative, set it equal to 0, find where it's undefined, okay? Now let's talk with me, let's talk again. When you look above here, you're like, oh my gosh, this is a chain rule, right? There's a quadratic inside my square root. And you're like, wow, okay, that's gonna be a mess trying to set equal to 0, okay? It's actually not, and here's why, okay? Isn't it true if I minimize x squared minus 23x plus 136? Anytime I minimize what's under the square root, it's going to minimize the square root, right? The square root of 25 is 5, right? The square root of 16 is 4. The square root of 9 is 3. Anytime I minimize just the quadratic expression that's under the square root, it will in fact minimize the whole square root, right? As every time the radican gets smaller, so does the square root. So all I actually have to do is minimize x squared minus 23x plus 136. If I minimize this, it will minimize the square root. And so I'm just taking the derivative of this expression. Isn't that much nicer? So that would be 2x minus 23. And now, instead of having a horrible chain rule and trying to set it equal to 0, my critical points, undefined, this is defined everywhere. Where is this equal to 0? It equals 0 at 23 halves. Okay. So that's a critical point, but I'm going to make sure it's actually a minimum, right? Because by using my first derivative chart, because I want to make sure it's a minimum, not a maximum. Okay, let's talk again. Here I am. Class, how do we know that this is in fact a minimum and not a maximum? Because I know what the maximum distance is between 12, 0 and a point on this graph. It's infinity. Right? As that square root keeps going and my point 12, 0 stays here, what's the maximum distance to any point on that square root? Infinity. It keeps going. So what I must have, this critical point must be a minimum distance. It must be. But let's go ahead and do the first derivative test so that you can see that. Okay, so let's go ahead. All right. Let's see, here's our interval. Our x, right, our x is going to go from 0, right? Would it be negative infinity? No, it wouldn't, because the square root, right, started at 8 here, right? So let's talk about that. I'm trying to find the x, so it wouldn't be less than 8, right? So we would start from 8. Again, if you put 0, like you say, well, I know it's on the positive side, not on the negative, that the x isn't negative, you'd be fine. But logically speaking, I see my x has to be at 8 or greater, right? So just trying to get us really thinking here. Up to 23 halves, and then 23 halves really to infinity, right? And let's do a test value. Let's call this 10. And let's just call this 20, right? There we go. And let's check that derivative. So when you check the derivative, when you put a 10 in, you get a negative. When you put a 20 in, you get a positive. And that, in fact, is a minimum. Okay, now, did we actually answer the question? Okay, we got x equals 23 halves. What they wanted us to do was find the point in this function that is closest to 12, 0. So I have the x part of the point, right? So let's just put the x part of the point in and get the y part of that point. And I promise you, like if you drew it out, that this point on this square root function right here, and that point 12, 0, when you connect them, it would be the closest, the smallest distance you would be able to find. Let's go ahead. Let's see. I'm going to put the 23 halves. 23 halves, I'm just going to call that 8 minus 16 halves, right? And so that would be the square root of 7 halves. Not pretty, but that is in fact a correct answer. There we go. Thank you for hanging out with me. And I hope you have a great day. I hope you find it as fascinating as me.